Good evening and welcome everybody. It's Obi-Wan Pez4 and Simplex Pachinko. We are going to be doing some Monday. What did I do? Math Communication Monday. Going to look first at the embarrassing problem of infinity that maybe Laurent said was not quite as embarrassing as everyone thinks it is. I was just also watching somebody rail on today about ultra finitism. That was a fun video. I believe that is the wrath of math, and watching his. My goodness, what's going on over there? Yeah, there we go. So that was Wrath of Math's video on why a particular ultra-finitist uh, is completely incorrect. The idea here being that well, pi is an incomputable number, so therefore went on some big rant. And basically, it's completely unnecessary, and even if we wanted to, like, I used an example of like cut a board to a particular size, whatever it is. Like, you're never really going to get it on any particular value. If you zoom in far enough, you're always going to see some sort of deviation from you're always going to see some sort of deviation from whatever value you were targeting. So it always seems like we're going to have to worry about, specific values in terms of like limiting processes. All right. So, when infinity stopped being embarrassing. The Doubly Infinite series of Pierre-Alphonse Laurent and the Mathematical Rehabilitation of Singularities by B. Sriram and N. Carjanto. For the better part of a century, isolated singularities, the points at which a complex function fails to be analytic, were treated as pathological obstructions requiring elaborate avoidance strategies. Pierre-Alphonse Laurent, 1813 to 1854, a French military engineer who pursued mathematics between port construction projects at Le Havre, ended this avoidance in 1843 by extending Cauchy's Taylor type theorem to doubly connected, i.e., annular domains, producing the doubly infinite power series that now bears his name. The conceptual shift was profound. Negative power terms in the expansion, far from signaling a breakdown of formalism, encode precise geometric information about the singularity. Laurent's contribution arrived through an unhappy institutional trajectory, submitted after a prize deadline, subjected to a priority claim by Cauchy that complicated the publication process, and issued in full only posthumously in 1863, yet it became indispensable to every branch of mathematics and mathematical physics that touches on complex functions. Complex function theory. Hey, famished. We reconstruct the mathematical theorem Laurent solved, place it within Cauchy's analytic program of the 1830s to 40s, examine the institutional failure that prevented publication from the Memoir, document the independent parallel proof by Weierstrass, 1841, published in 1894. My goodness, 53 years after he apparently proved it, and trace the series' subsequent absorption into the standard toolkit via Briot and Bouquet, Weierstrass's systematic treatment, and the residue calculus. Drawing on Laurent's 1843 Compte Rendu notice, Cauchy's Academy report of the same year, Joseph Bertrand's memorial notice, read 1860, published 1890, and the peer-reviewed secondary literature, Neuenschwander, 1978, 1981, and Manning, 1975, Bottazzini, 1986, Gray, 2015. We also analyze the modern philosophical significance of the series, which we term exile mathematics, and survey its reach into perturbation theory, number theory, probability theory, and quantum field theory. Readers familiar with the theorem but not its institutional history will find here a documented account of why a foundational result was withheld from publication for 2 decades and how it nevertheless achieved canonical status. Once you take care of the dogs, nice. Systems of equations in 2 variables, yep. Yeah. I tended to like doing it even after I learned how to solve it using matrices and row operations. I often still like to, piece the puzzles together, and for the most part, it's still like as soon as I started teaching it, it was pretty much all we're going to be doing this via the elimination method, so getting rid of variables, which is really just the same as doing it with matrices and row operations. However, if there is an equation that is set up already with one of the variables either solved for or easily solved for, i.e., it's just like apparently that failed to send. Okay, interesting. Cool. If anybody did not get the arXiv, there you go. That's the link if you want to see this particular paper on your own. I feel like, yeah, there we go. Page width. There we go. A. Okay, so color key. Key milestones in the history of the Laurent series. Blue is a mathematical development. Red is institutional and biographical event. Green is the textbook canonization. And this orange color is the application to physics. So we have Taylor, who wrote Methodus in 1715, did the power series framework. Cauchy in 1825 wrote the integral theorem and introduced the concept of residues. Cauchy, Cauchy Memoirs, 1831 to 33, and analytic program, calcul des limites. Yeah, I couldn't tell there for a second if I was supposed to be reading French or not. It's fine. Cauchy exercises, 1840, mean value annular condition, closest precursor. Weierstrasse, 1841, annular expansion proved in manuscript, but was unpublished. Laurent, 1843, doubly infinite series submitted, compte rendu notice, but withheld for approximately 20 years until 1863, when it was published posthumously in the Journal École Polytechnique. Meanwhile, Briot and Bouquet, 1856, residue calculus founded on the Laurent series. Then, Casrati Teorica, 1868, Italian reception. CW. Cauchy-Weierstrasse. Theorem proved. Hermite-Sorbonne lectures, 1870s. Weierstrassian tradition enters France. Weierstrasse, 1876, singularity classification via Laurent series. Hulda, 1882, removability lemma isolated, clean. Finally have a clean Cauchy-Weierstrasse proof. Weierstrasse, 1841, MS published Mathematica Werke, 1894. Whitaker and Watson, 1902. Goursacourt, International Canon. And QFT. Now, I don't know what that is supposed to be, but it just looks like it's an apostrophe kind of stuck in the middle of nowhere with a T. Uft und Weltmann, 1972, Laurent series in dimensional regularization, i.e. QFT. Now, I don't particularly know what that means, but that's alright. Yeah. Alright. The mathematical inheritance, Taylor, Cauchy, and the limits of positive powers. Mathematics has always had a problem with infinity. Not the tame infinity of limits approaching a finite value, but the explosive infinity that erupts when a function encounters an isolated singularity. Brooke-Taylor formalized the standard remedy in the early 18th century. Taylor, 1715. Take any smooth function, determine its derivatives at a base point C, and use that local data to build an infinite polynomial approximation. For a function f analytic in the open disk, d of c comma r, right, from the base point C, and r being our radius of convergence. Disk, yeah, d of c comma r is equal to the set of all complex numbers z such that the distance between z and c is less than r, the radius. The Taylor series, f of z is equal to the infinite sum as n goes from 0 to infinity of a sub n times z minus c to the n, where a sub n is equal to the nth derivative of f at c divided by n factorial. Converges absolutely and uniformly on every compact subset of d of cr. The radius of convergence r is precisely the distance from c to the nearest singularity of f. For an entire function like e to the z, the series converges everywhere. So e to the z is equal to the infinite sum as n goes from 0 to infinity of z to the n over n factorial, which is just 1 plus z squared over 2 factorial plus z cubed over 3 factorial, etc. The conceptual breakthrough that made a solution possible came from taking seriously the geometry of complex numbers, Needham 2023. Throughout the 18th century, mathematicians had grown increasingly comfortable working with I equals the square root of -1, initially as a purely algebraic device for solving equations that had no real solutions. What emerged gradually, becoming fully explicit only in the work of Gauss, Argand, and Cauchy in the early 19th century, was that complex numbers are not merely numbers but coordinates in a two-dimensional plane. Every complex number, c is equal to x plus iy, corresponds to a point whose horizontal displacement from the origin is the real part x, and whose vertical displacement in the imaginary part is the imaginary part y. This geometric interpretation transformed the study of complex functions. The function f, mapping c onto c, is no longer just a formula to be evaluated. It is a mapping between planes, a geometric transformation of the complex plane onto itself. Analytic functions, those satisfying the Cauchy-Riemann equations, are precisely the mappings that are locally conformal. They preserve angles and scale uniformly in every direction at non-critical points. From this vantage point, the singularity is not a place where the function breaks down, it is a place where the function does something geometrically distinguished, where the local scaling bond becomes where the local scaling becomes infinite, where the mapping wraps a neighborhood of the singular point around itself infinitely many times. Singularities, viewed geometrically, are not defects but features. They carry precise topological information about a function's global behavior. Cauchy, working in Turin, the capital of Sardinia, where he held the chair at the university after his voluntary exile from France in 1830, produced in his Theorem Memoirs of 1831 to 1833, Calcul des limites, and the earlier 1925 memoir on definite integrals. A geometric theory of complex integration for Cauchy's rigorous analytical program. More broadly, see Grabner 1981. Cauchy's integral theorem establishes that the integral of a function analytic on and inside a simple closed contour gamma vanishes identically. So the contour integral on gamma of f of z dz is going to be equal to 0. When f has isolated singularities inside gamma, this vanishing breaks down in a controlled way described by the residue theorem, a consequence of Cauchy's framework that would later find its natural home inside the Laurent expansion, see section 5.2. So the contour integral on gamma of f of z to z is equal to 2 pi I times the sum of all k's of the residue of f on z sub k, where the sum runs over all singularities z sub k enclosed by gamma. Singularities were, in Cauchy's hands, information carriers rather than mere obstacles. Yet Cauchy's framework contained a structural restriction he did not fully resolve. Equation 1 requires f to be analytic on a simply connected region containing C, as shown in figure 1. A disk with no holes creates an explicit geometrical constraint. Right? There's stuff outside, there's stuff inside. We don't really... At this point, we're not really talking about the stuff that is on the circle itself. Because here our Taylor series is going to diverge when the distance between Z and C is greater than R. And so this is our region of convergence, D of CR. And then R is equal to, right? It's just the same. Wow. As shown in figure 1, a disk with no holes creates an explicit geometrical constraint. The Taylor series lives inside a disk whose radius is fixed by the distance to the nearest singularity, and it cannot be extended beyond that boundary by any manipulation of the series itself. The moment one attempts to work in a doubly connected region, a domain with a hole, such as the annulus, A of C, R and R, is equal to the set of all z in the complex, such that the distance between z and c is between lower r and bigger R. Or the punctured neighborhood, where the distance between 0 and epsilon of an isolated singularity. The Taylor expansion becomes undefined at the foundation. When C is itself a singularity, there is no finite value f of C from which to form the Taylor coefficients. Nth derivative of f at C over n factorial. Very first step of the construction fails. A function as simple as 1 over z demonstrates the impasse immediately. It is the only natural expansion point near the origin. A function as simple as 1 over z demonstrates the impasse immediately. Its only natural expansion point near the origin is the origin itself. And yet 1 over z is not even defined there. Taylor series is not merely inaccurate in such a region, it is inapplicable. This limitation was not merely abstract. By the early 1840s, special functions of applied importance, most notably Bessel functions and elliptic functions of Jacobi, were known to possess isolated singularities, and the problem of representing such functions as series near singular points was pressing. Bottesini and Gray. Taylor's theorem offered no traction, something genuinely new was required. It is worth delimiting precisely what was new, since negative power terms in series expansions were not known before 1843. Euler in Introductio in Analysin Infinitorum, 1746. Boy. I don't dare unplug the internet cable from the wall in order to move it from above to below a pile of other cables. So we're just going to have to deal with 34 inches tall, despite not quite matching up with the, you know what, that's fine. Yeah, you can see this is one of my grandmother's pictures. She's an artist from Maine. That was a painting that she did in watercolor when she was out in California. Been there for a while. Like late 90s, early 2000s. Oh, 04. Okay. So, just double check real quick. Got everything? I think so. Should be alright. Alright. It is worth delimiting precisely what was new, since negative power terms and series expansions were not unknown before 1843. Euler in that, and throughout his operational work, freely manipulated series containing negative powers of the variable, obtaining expansions such as 1 over 1 minus x is equal to the negative sum of x to the negative n as n goes from 1 to infinity for all absolute value of x greater than 1. By algebraic inversion of standard power series. These are genuine negative power expansions, but they are case-by-case algebraic manipulations. Euler treated power series as what Memoir calls non-terminating polynomials, deploying them as universal formal tools without an integral formula for coefficients, a proof for convergence, or a concept of an annular region such as a natural validity domain. See Remer 1991. The transition from these Eulerian identities to the residue theory of the 1840s required a fundamental shift in perspective, from the expansion of the specific algebraic expansions to the representation of any function satisfying the condition of analyticity. What Euler's formal manipulations lacked, and what Cauchy's residue theory extracted only partially, was a systematic framework in which negative power calculations could be rigorously determined for an arbitrary analytic function on a prescribed domain. It is precisely this gap that Laurent's 1843 result filled. See Grabiner in 1981, Remer 1991. Cauchy and his theory of residues, developed through the 1820s and 30s, extracted from the singular behavior of a function the single number residue of f comma c is equal to 1 over 2 pi I times the contour integral at along gamma of f of zeta d zeta, which in Laurent's language is the coefficient a sub negative 1. But Cauchy obtained this through his history of extraordinary integrals without asking what the remaining negative power coefficients a sub negative 2, a sub negative 3, etc. were, or whether they formed part of a systematic series of representation valid on a definite domain. In his Turin memoirs of 1831 to 33, Cauchy worked with a series in annular regions as convergence conditions, but not as the natural habitat of a doubly infinite expansion. See Bottazzini and Gray. The transition from Euler's formal manipulations to Cauchy's regime of precise domains and convergence criteria marks the intellectual context within which Laurent's problem became both formulable and necessary. See Grabiner and Remer. What was genuinely new in Laurent's 1843 result was the combination of all three elements on that antecedent literature that the antecedent literature lacks simultaneously: a general representation theorem valid for any function analytic on any annular domain, with integral formulas for all coefficients a sub n, including all negative orders expressed as contour integrals over any simple closed curve lying in the annulus. This combination and not the isolated appearance of negative powers that constitutes the advance. Alright, section 2, Laurent's discovery, the memoir, and its mathematical content. The engineer-mathematician Pierre-Alphonse Laurent. He was born in Paris on 18th of July 1813 to an Anglo-French family. He entered École Polytechnique in 1830, graduated in 1832 as one of the strongest students of his year, subsequently trained as a military engineer at École d'Application in Metz in the Moselle department of northeastern France. After active service in the Algerian campaigns in 1830, Algeria then being under French military occupation since the invasion of 1830, including the Tlemcen expansion in northwestern Algeria near the Moroccan border and the Tafna campaign against Abd el-Qadir. He returned to France around 1840 and spent approximately 6 years directing the hydraulic engineering works for the enlargement of the port of Le Havre in the Seine-Maritime department in the Normandy region of northern France, transforming it into France's principal seaport. Biographical fact that matters mathematically is this: Laurent's major result was produced while he was managing large-scale harbor construction, not while holding a university post. Seems strange, doesn't it, that these guys have a lot of ability to make discoveries not when they're in an office. Or rather, in the case of Einstein, it was a patent office. And in the case of my former teacher, Yitang Zheng, it was, no, Zheng Yitang. It was while he was on vacation. Joseph Bertrand, in his memorial notice read before the Société des Amis des Sciences in April 1860, is the most nearly contemporaneous scholarly source on Laurent's working conditions. He records that Laurent's superiors held his practical engineering judgment in high regard, which only underlines the intellectual force of the theoretical work he was producing simultaneously while stealing hours from sleep. His professional life and his mathematical research were not two separate activities. The questions engineers asked in the 1840s about elasticity, wave propagation, heat equilibrium, potential theory were precisely those whose mathematical formulation involved analytic functions near singularities. Laurent's result did not arrive despite his engineering context. It arrived in part because of it. In 1843, Laurent submitted a memoir to Grand Prix competition of the Académie des Sciences, whose topic had been announced at the Academy's public session of 13th July 1840, defined in the original French, les équations aux limites que l'on doit joindre aux équations indéfinies pour déterminer complètement les maxima et minima des intégrales multiples, to find the limiting equations that must be joined to the indefinite equations in order to determine completely the maxima and minima of multiple integrals. Ita Cauchy. Prize was awarded to Pierre-Frédéric Sarru. A memoir by Delaunay received honorable mention. Cauchy's report on Laurent's submission noted that both Laurent and Sarru had independently established the same formulas of integration by parts, expressed in different notations, and that Laurent had used methods analogous to those of Sarru to obtain the limiting equations. Now, I am interested in that one. Oeuvres. Okay. Curious. It's going to be in French, isn't it? Yep. Okay. Well, we're not going to be able to read that actually. But worth a shot. English translation. No. Yeah. Silly me. I thought that one, because it said by in there, would be in English. Um. Hmm. Yeah. Getting access is going to cause me to. Yeah. I have to log in. Yeah, no. Alright, well, whatever. uh, For the translation of the essential part of this report, see Todd Hunter. It's probably also not. But hey. Hey. Of 583, 476. Let's see if that's actually accurate here. Memoir on the Calculus of Variations was written by Laurent in competition for the prize offered by Academy of Sciences at Paris. See Article 133. Laurent's memoir was sent to the Academy just after the time fixed for the reception of the memoirs, but before the judges had published their award. A report on Laurent's memoir is given by Cauchy in the Compte Rendu. We will give a translation of the essential part. The application of the calculus of variations to the investigation of the maxima and minima values of multiple integrals required especially new formulae of integration by parts and a new notation which should afford an easy expression of these new formulae. The judges of the prize had particularly noticed the paragraphs relating to these two objects in the memoir of Saru. The corresponding paragraphs in the memoir of Laurent were also of worthy notice. The two authors have employed different methods of establishing the formulae of integration by parts. But the formulae are in reality the same in the two memoirs, though they are expressed by two distinct notations. We may add that when once these formulae are established, Laurent uses methods analogous to those of Saru in order to obtain the limiting equations. The memoir of Laurent contains, besides some observations which are not without interest respecting the different ways of verifying the limiting equations. We will not conceal the fact that among the methods employed by Laurent some may be considered rather as methods of induction than perfectly rigorous methods, but it is generally very easy to verify the exactness of the results obtained by these methods, as the calculations commonly can be easily effected. To sum up, we think that the memoir of Laurent deserves to be approved by the Academy and to be inserted in the Recueil des Savants Étrangers. We may add that the memoir does not seem to have been printed as of yet. There is a report on two memoirs by Laurent in Compte Rendu. The report is by Cauchy and gives a short account of the scientific labors of Laurent, and then recently deceased. All right. In case anybody wants to read that. Plenty more book where that came from. All right. All right. Laurent's memoir submitted after the competition closed, but before judges announced their decision, was therefore composed without any knowledge of competing memoirs, a circumstance that underlines the independence of his work. This memoir bears the title Memoir sur les calculs de variation and is distinct from the separately submitted memoir on the Laurent series theorem titled Extension du Theorem de M. Cauchy relatif à la convergence du développement d'une fonction suivant les puissances ascendantes de variables. Cauchy, 1843. Previous one from Ital, 1973. Which was reported to... Right, the Cauchy one was reported to the Academy on 30th of October, 1843. Both memoirs received Cauchy and Louisville's recommendation for publication in the Recueil des Savants Étrangers. Neither was published during Laurent's lifetime. The memoir on the Laurent series Theorem was never published. No manuscript copy has ever been located in the published secondary literature. Its mathematical content survives primarily through Cauchy's report to the Academy of October 1843, which quotes Laurent's own statement of his result. Cauchy's report appears in the Compte Rendu Hebdomadaire 17 and is the closest we have to Laurent's own words. The report is also valuable because it preserves on the preceding page Cauchy's own statement of his earlier theorem, in which Laurent was explicitly extending. The juxtaposition of the two statements reveals the precise conceptual distance between them. Cauchy's theorem reads in the original French, X désignant une variable réelle ou imaginaire, une fonction réelle ou imaginaire de x sera développable en une série convergente ordonnée suivant les puissances ascendantes de cette variable, tant que le module de la variable conserva une valeur inférieure à la plus petite de celles pour lesquelles la fonction ou sa dérivée cesse d'être finie et continue. Finite and continuous there at the end. X designating a real or imaginary variable, a real or imaginary function of X will be developable in a convergent series ordered according to ascending powers of that variable, so long as the modulus of the variable retains a value less than the smallest of those for which the function or its derivative ceases to be finite and continuous. 3 words carry the entire weight of the extension, where Cauchy writes une série for one series, ordered according to the puissance ascendante, ascending powers, with the modulus bounded above by a single limit, the geometry of a disk. Laurent writes la somme de deux séries, the sum of 2 series, one ascending and one descending, with the modulus comprised entre deux limites, between 2 limits, i.e. the geometry of an annulus. The move from one series to 2, from ascending powers only to ascending and descending, and from a disk to an annulus, is the entire theorem. In Laurent's formulation, as preserved in Cauchy's report, X désignant une variable réelle ou imaginaire, une fonction réelle ou imaginaire de X pourra être représentée par la somme de 2 séries convergentes ordonnées l'une suivant les puissances entières et ascendantes, l'autre suivant les puissances entières et descendantes de X, tant que le module de X conservera une valeur comprise entre 2 limites entre lesquelles la fonction ou sa dérivée ne cesse pas d'être finie et continue. X designating a real or imaginary value, a real or imaginary function of X will be representable by the sum of 2 convergent series ordered, one according to the whole and ascending powers, the other according to whole and descending powers of X, so long as the modulus of X retains a value comprised between 2 limits, between which the function or its derivative does not cease to be finite and continuous. In the notion that became standard after Weierstrasse systematized the theory, what Laurent is proved is the following. Right. Theorem 1, let F be analytic on the annulus A of C, R and R, or small and big, is equal to the set of all Z in complex, such that the distance between Z and C, that is the value that we picked, Z, the value for the function, minus C, the location of the center, must be between little r and big R. Then F emits the unique representation. F of Z is equal to the summation as n goes from negative infinity to positive infinity of a sub n times the quantity Z minus C all raised to the n, converging absolutely and uniformly on every compact subset of A of C R R. The coefficients are given by a sub n is equal to 1 over 2 pi I times the contour integral on gamma of f of zeta over zeta minus c to the n plus 1 d zeta, where gamma is any simple closed curve in A encircling C once counterclockwise, winding number plus 1, or in theory clockwise with a winding number of -1, probably. The series 3 separates into two parts, figure 2. The analytic part, or regular part, n goes from 0 to infinity of a sub n times z minus c to the n, converges for z minus absolute value z minus c less than r, and resembles a Taylor series. The principal part, summation as n goes from 1 to infinity of a sub negative n of z minus c to the negative n, converges for absolute value of z minus c greater than little r, and encodes the singular behavior. Together they converge on the full annulus, as seen here. When the inner radius r equals 0, a punctured neighborhood of C, the behavior of the principal part determines the nature of the isolated singularity. See section 5. The Laurent annulus, figure 2, shaded. Solid circle is the outer boundary, dash circle is the inner boundary, contour gamma is in red. Simple closed curve. To emphasize that theorem 1 holds for any such curve lying in the annulus and encircling C once counterclockwise with the winding number plus 1, not merely for circular contours. Representative for the annulus is marked. Coefficients are independent of choice gamma. To see the theorem at work concretely, consider f of z is equal to e to the z over z squared, which has a singularity at the origin. Dividing by the exponential series z squared. Right, so e to the z over z squared is equal to 1 over z squared times, that's the Taylor expansion of e to the z. Principal part is z to the negative second plus z to the negative first. The regular part begins with the constant term 1/2. Coefficient a sub n minus 1 is 1, which is going to be the residue of f at z equals 0. All right, we'll come back for the barrier argument. Thank you so much, everybody, for coming, and we'll be back in about 3 minutes, give or take. So get up, stretch, cycle that water, do what you need to. We'll see you in a little bit. Thanks so much. Alright, welcome back everybody. So we have the barrier argument from doubly connected domains to doubly infinite series. Preliminary remark on the sources is essential. Laurent's 1843 Compte Rendu notice is 2 pages in length and states the extension theorem without proof. Full memoir on the Laurent series theorem from which that notice was extracted and was submitted to Académie des Sciences in 1843, reviewed by Cauchy and Liouville, and then following the institutional failure described in section 3, never published. It is effectively lost. No manuscript copy has been located in the published secondary literature. The proof technique attributed to Laurent in what follows is therefore a scholarly reconstruction, not a transcription. Primary basis is Cauchy's report to Academy of October 1843, which, while written to assert Cauchy's own priority, nonetheless preserves Laurent's statement of his theorem in his own words and gives some indication of the methods involved. The barrier argument presented below represents the consensus reconstruction in the secondary literature by Neuenschwander, Bottizzini, and Gray, or as seen in those 3. No published alternative interpretation of Laurent's proof method has ever been proposed. One caveat is necessary. Cauchy's appended note to the same report presents its own derivation of Laurent's theorem via the mean value theorem for analytic functions, i.e. f of c is equal to 1 over 2 pi times the integral from negative pi to pi of f of c plus r e to the ip dp, which is Cauchy's preferred approach rather than Laurent's. This is documented by Bottizzini and distinguished from Laurent's reconstructive method in Neuenschwander. The reconstruction that follows reflects Laurent's method as inferred from the structure of his results, not from Cauchy's reformulation. Reconstructed proof runs through a direct application of Cauchy's integral formula to doubly connected domains. The key geometric step is a barrier argument. Figure 3. Radial cut connects the inner and outer boundary circles, converting the doubly connected annulus into a simply connected region. Cauchy's formula is then applied, and the contributions along the 2 sides of the cut cancel. The integrand is analytic along the cut, and the 2 sides are traversed in opposite directions. This leaves contour integrals along the 2 circular boundaries, expanding f of zeta over zeta minus z geometrically in powers of z minus c over zeta minus c on the outer circle, where the distance between zeta and c is greater than the distance between z and c, and in powers of zeta minus c over z minus c on the inner circle, where in this case the distance between zeta and c is less than the distance between z and c, which produces the 2 convergent series whose sum is 3 with coefficients 4. What's that? Right. The sum is this f of z sum here, and the coefficients are represented by a contour integral. Okay. Should be noted that in 1843, neither the language of simply nor doubly connected domains nor the full topological machinery was available. Those concepts would be made precise only in Riemann's 1851 dissertation. What Laurent and Cauchy worked with was more informal notion of a region bounded by two curves. The barrier argument was a standard device in Cauchy's own practice. Laurent's innovation was recognizing that applying the barrier argument to an annular region necessarily produces a series with both positive and negative powers, not merely the non-negative powers of Taylor's theorem. See Neuenschwander. The topological clarification of multiply connected domains and its interaction with the Laurent series in the Weierstrass tradition is traced in detail in Botticelli and Gray. Archives de l'Académie des Sciences in Paris holds the Pochette de Séance and Grand Prix competition papers for 1843, and the Service Historique de la Défense in Vincennes holds the papers of the Corps du Génie in which Laurent served, are the repositories where a surviving manuscript would most plausibly be found. A full archival search lies beyond the scope of the present article. The claim of loss follows Itard and is confirmed by Neuenschwander and Botticelli, all of whom work exclusively from published sources. The manuscript presents the barrier argument as the consensus reconstruction of Laurent's proof method. It is worth noting that the history of proofs of Laurent's theorem is itself varied. Remer documents that Alfred Pringsheim attempted an integral free proof via mean values, following the same methodological preference that motivated Cauchy's own 1843 note, while Ludwig Schaefer gave a reduction of Laurent's theorem to the Cauchy-Taylor theorem that, though ingenious, Remer characterizes as a Baroque route not recommended for teaching, since it ultimately depends on the Cauchy interval formula anyway. These alternative proof strategies illuminate why the barrier argument, despite its reliance on integration, became the standard pedagogical presentation. The institutional failure. Cauchy's report and priority claim. Cauchy and Liouville were appointed to review Laurent's memoir. Liouville was not a disinterested administrator in his role, but Botticelli documents that he himself began to study doubly periodic functions in the summer of 1844, the year immediately following the review, and his subsequent lectures at the Collège de France on this subject would later inspire Briot and Bouquet, as documented in section 3.2. Both recognized its merit and jointly recommended publication in Recueil des Savants Étrangers. What happened next became one of those episodes that punctuate mathematical history. The sequence of events is significant. Gray documents that Cauchy made his priority claim at the Academy meeting immediately following Laurent's submission, before he had even submitted the official joint report with Liouville, asserting that earlier results from his Exercices de Mathématiques of 1826 and Exercices d'Analyse of 1840 gave him priority over Laurent. That joint report was presented only on 30th of October 1843. appended to the joint report a personal note whose opening sentence reads: La rapporteure a joint à ce rapport la note suivante qui indique la manière la plus simple d'arriver au théorème de M. Laurent en partant des principes établis dans les exercices d'analyse et de physique mathématique. The reporter had appended a note indicating the simplest way to arrive at M. Laurent's theorem, stating from principles already established in Cauchy's own earlier exercises, implying that Laurent's result was not original but derivable from existing work. The intellectual authority Cauchy invested in his exercises as a foundation for the whole of analysis is documented by Grabiner. The claim was, at a minimum, difficult to sustain on the mathematical evidence, even though Gray documents that Cauchy had proved a uniqueness theorem for series containing negative powers as early as November 1841. The existence of such prior work does not bridge the conceptual gap between Cauchy's results, which concern convergence conditions, and Laurent's theorem, which concern the representability of an analytic function on an annular domain by a doubly infinite series with explicit integral formulas for all coefficients. It is worth noting that in 1843, Cauchy had not yet arrived at the precise definition of a complex analytic function that his priority claim implicitly required. Gray argues that Cauchy only fully recognized the role of the Cauchy-Riemann equations and the concept of analyticity as late as 1851, though Botticelli's account suggested the recognition was more gradual, developing across the 1840s as Cauchy progressively refined his understanding of what conditions a function must satisfy to admit to a power series representation. On either reading as conceptual apparatus required to fully justify the priority claim that was not in place at the time Cauchy made it in 1843. As Neuenschwander observes, Laurent's theorem genuinely extended the Cauchyan framework in a non-trivial direction. Cauchy's results concerned series in ascending powers of the variable on simply connected domains. Laurent's results concern doubly infinite series on annular domains, which are doubly connected. The formal gap between the two is not a matter of routine reformulation. It requires the barrier argument for doubly connected regions that Cauchy had not made systematic. Freudenthal, in his authoritative biography of Cauchy, states plainly that Cauchy had simply failed to discover Laurent's theorem, a judgment that aligns with Neuenschwander's and Gray's assessments of the mathematical non-triviality of Laurent's contribution. Kronecker's judgment was more dismissive still. Bremer records that he remarked the Laurent expansion was an immediate consequence of Cauchy's integral theorem and therefore useless to credit to any specific author. A verdict that, whatever its merits and priority adjudication, underscores how thoroughly the result had been absorbed into the standard apparatus of complex analysis by the late 19th century. Historians had not been unanimous in their assessment of this episode. Neuenschwander and Gray emphasized the mathematical non-triviality of Laurent's extension and the unjustifiability of Cauchy's priority claim on strictly mathematical grounds. Gray is more direct in his assessment, describing Cauchy's response as characteristic of his habit of taking the work of others as an opportunity to promote his own. Bellost's biography of Cauchy, however, states the episode within the norms of the Académie des Sciences in 1840s, where senior mathematicians routinely appended priority notes to referees' reports, and where such behavior was not regarded as improper by the standards of an institution. The Academy's refereeing and publication procedures in this period were documented in detail by Gratin-Guinness. And on this reading, Cauchy was acting within accepted practice. however, damaging the consequences for Laurent. Bottini further notes that the Academy's publication practices on this period were slow and unpredictable, regardless of any individual intervention, and that Laurent's late submission, which arrived after the completion deadline, had no formal standing under the Academy's own rules, complicating any simple causal account as to why the memoir was never published. Freudenthal's analysis of Cauchy's habitual working method is instructive here. He documents that Cauchy routinely used his role as referee to republish authors' results in broadened form, noting that all his own prior related work in the report behavior he characterizes as standard rather than the exceptional for Cauchy. The full picture is therefore one of overlapping institutional constraints rather than single decisive act. Cauchy's priority note, the late submission, the Academy's publication procedures, the loss of the manuscript all contributed to the outcome. Nonetheless, with Cauchy's intervention having complicated the priority question while he simultaneously served as a primary referee, the outcome was paradoxical. The Academy formally adopted the conclusions of the joint report, accepting the recommendation to insert Laurent's memoir into Recueil de Savants étrangers, yet no publication followed. The complete memoir was lost. What Laurent published in his own lifetime amounts to a single 2-page notice stating the extension without proof. The full memoir, with proofs and elaborations, never appeared in print. Gray notes that when the same misfortune befell a second paper, Laurent turned to applied mathematics, pursuing research in mathematical physics until his death in 1854. The irony is sharp. Cauchy published more than 800 papers, became one of the most celebrated mathematicians of his era, yet it is Laurent's name, not Cauchy's, that every student of complex analysis encounters first. Bertrand, writing in retrospect, captured the asymmetry. Where Cauchy's genius lay in part in his extraordinary productivity, what distinguished Cauchy was that he informed the public of them minutely and at length. The Laurent series, the Laurent expansion theorem, Laurent polynomials, these concepts bear his name because his contribution genuinely extended mathematical capability in a way that could not be ignored, whatever the institutional obstacles it encountered. All right. I think I'm gonna call it there. We'll come back to this next week. Just not feeling it right now, so shall return. Let's go see Xander if he's still. Yeah, he's still going. So Xander is doing Ace Attorney. I hope you all are having a good week so far. We will head over to, we'll head to Xander's, and then tomorrow we'll be doing more blueprints, and then on Wednesday we'll come back for a calculation night. So come in with your questions, whatever it might be, and thank you so much everybody for coming. My name's Obi-Wan Pez. This is N Simplex Pachinko. Have a good night.